Assalamualaikum, very good day to everyone. This is GTK 209 Engineering Control Design Topic 8 Engineering Control for Hazard. My name is Dr. Khairilmizal Samsudin. You also know me as Dr. Mizal. My email and my phone number is as stated in the slides. In this session, we will look at chemical dispersion modeling. What will be the learning outcome? We want to understand potential sources of major accident and to differentiate effects from hazardous substance accident. For a hazardous substance, there are three possible outcomes, which is the thermal effect, the explosion effect, and the toxic effect. So how hazardous substance can lead to these three outcomes? A hazardous substance is stored in facility in several ways. Normally, it stores under a pressurized or a non-pressurized situations. A pressurized situation is normally above 1 bar. Our normal atmosphere is 1 bar. So a pressurized situation is above 1 bar. And for a non-pressurized situation, it's lower than 1 bar. In a pressurized situation, a hazardous substance can be in three phases, which is a gas phase, a liquid phase, but there are possibility that this hazardous substance be in both phases, which is gas and liquid. For example, if you have an LPG tank at home in the kitchen for the stove, normally in the tank, the LPG when it come out is in a gas phase, but within the tank itself, it's actually stored in a two phase, which is a liquid and a gas. For a non-pressurized hazardous substance, due to the current condition, normally it's in a liquid phase. And other such as a pyrophoric material can lead to immediate external fire or explosion if exposed to air. For a pressurized gas hazardous substance, if there is a leak of the hazardous substance itself, it can lead to a three outcome. Either a fireball, a jet fire, or if the chemical is not caught in an ignition, it will disperse. Or if the chemical is not flammable and it's toxic, it will disperse into the air. A liquid pressurized hazardous substance can also lead to a jet fire because when there's a leak, the liquid are sprayed into the environment and it causes a jet fire event. A two-phase pressurized hazardous substance, when there's a failure in the container or the storage tank, it will cause a flash and a rain out situation. If it's not a flammable material, because even if flammable material but not ignited, it will disperse. A non-pressurized hazardous substance, which is normally in a liquid form, if exposed to a hazardous situation, if the chemical itself is flammable, it can cause a pool fire within the storage facility. However, if the liquid is easily evaporated, it will lead to a dispersion scenario. It will disperse the hazardous substance into the air. There are three types of dispersion. It can be a jet dispersion due to the pressure. It can be a heavy dispersion due to the heavy gas, meaning to say that the vapor that disperses from the chemical stays on the ground. Or it can be a neutral dispersion if the density of the vapor is the same as the air or lighter, so it will disperse into the atmosphere. However, if it's a dispersion of a flammable material, if it's ignited, it can cause a two possible event, which is a flash fire or a vapor cloud explosion. For other situations where the storage is heated by external fire, it can lead to oblivion, boiling liquid, evaporation, vaporization, explosion. Or this hazardous substance may explode due to a condensed situation, a runaway reaction like what we see in Cerveso, a dust explosion which is caused by a dust within the air which is ignited, or a normal physical explosion. Each of these outcomes will have a different modeling or a different consequence modeling where we can estimate the extent of damage and losses towards the community, towards the facility, and more. The outcome can be a thermal effect, which include jet fire, fireball, flash fire, pool fire, explosion, which can be a vapor cloud explosion, or oblivion, boiling liquid vaporization explosion, or a toxic effect dispersion, jet dispersion, heavy dispersion, or neutral dispersion. Let's look at some of the details. A flash fire is when a flammable vapor cloud encounters an ignition source. The cloud can catch fire and burn rapidly. The potential hazard that comes from a flash fire is a thermal radiation, smoke, and toxic byproduct from the fire itself. However, flash fire is non-explosive combustion of a vapor cloud. For example of flash fire, if you have a stove in the kitchen and you try to ignite it and then you have a fire at the stove. So this is an example of a controlled flash fire. However, a vapor cloud explosion is when a flammable chemical is released in form of vapor cloud. It is exploded when there is an ignition within the flammable range of the upper explosion limit and lower explosion limit, meaning to say here the mixture of the fuel and the air within the atmosphere is in a rich condition where it will explode if there are a source of ignition. It can be in a time of deflagration or detonation. However, the severity depends on the chemical itself, the cloud size, the type of ignition, and the congestion level inside the cloud. The primary hazard here for the vapor cloud explosion is the overpressure and hazardous fragments. Like I said earlier, if we take example of the gas stove, there are several times when we try to ignite this gas stove, it will not ignite. It will just let out the gas. However, suddenly, if we able to ignite this stove, it started a deflagration or detonation from this point, and the flash of the fire will come up to this area. This is an example of vapor cloud explosion. As you can see in this picture, this is the origination of the explosion, but the gas already filled in this area from here, and here is the source of ignition. The explosion will happen from here to back to the origin of the fuel source. So during an explosion, what will happen is there will be a slow deflagration, a fast deflagration, detonation, and a shoot of explosion here. And then there will be a stable fire, which we call it as stable detonation. Like what we discussed in the stove, after this initial detonation, then it will burn normally. The stove will burn normally. Let's look at the example of vapor cloud explosion.
June 21st, 2019. The Philadelphia Energy Solutions Refinery in Philadelphia, Pennsylvania. At 4 a.m., flammable process fluid containing mostly propane, along with a small concentration of highly toxic hydrofluoric acid, or HF, escaped from the refinery's HF alkylation unit, likely through a ruptured pipe elbow. The alkylation unit produced components of high-octane gasoline. The leaking process fluid formed a large ground-hugging vapor cloud that surrounded some sections of the unit. 2 minutes later, the cloud ignited, causing a massive fire. A control room operator quickly took steps to prevent the release of additional HF by rapidly draining the unit's hydrofluoric acid to a special vessel designed to hold the acid in the event of an incident. At 4:15, during the ongoing fire, an explosion erupted in the alkylation unit. 4 minutes later, a second explosion occurred. At 4:22, a process vessel in the unit containing flammable hydrocarbons violently ruptured, causing the largest explosion. A large 38,000-pound fragment of the vessel flew across the Schuylkill River and landed on the river's opposite bank. 2 other fragments, one weighing about 23,000 pounds and the other about 15,500 pounds, landed inside the refinery. The fire burned for over 24 hours until it was finally extinguished the following day at about 8:30 a.m. 5 workers sustained minor injuries during the incident and response. The CSB is unaware of anyone experiencing health impacts from the hydrofluoric acid release.
Pool fire. A pool fire occurs when a flammable liquid forms a puddle on the ground and catches on fire. In some cases, heat from the pool fire may weaken a leaking tank and cause a fail completely. So, this is an example of a pool fire. Normally, this happens in oil and gas industries, where they store oil in storage tanks. In a pool fire situation, if there are not enough cooling of the tank itself will melt. For example, as what you can see here, the failure of the storage from the pool fire are causing the melting of the tank and later on causing the whole area caught on fire. This is an example of a pool fire happened in Malaysia a few years back. As you can see here, the fire happened within the tank. If you look closely, you can see that several emergency responder here is spraying water on the other tank. Why? Because they want to prevent this tank from catching fire. The hazardous material, which is the flammable material within this tank, to auto-ignite due to the radiant heat from this fire. Jet fire. A jet fire is a flammable chemical which is rapidly released from an opening and immediately catches fire. A two-phases jet fire occurs when a gas that has been liquefied under pressure is released. So it causes a jet fire. Because the liquid is evaporated and as it escapes, the chemical is released as an aerosol spray. We also know this as a flamethrower. As you can see here, for some chemical, we will not see the degree of the flame itself. This is an example of a jet fire. This is a jet fire when an LPG tank bursts.
The flamethrower.
But the LPG tank didn't burst completely, it just burst at a single point within the LPG tank. Oblivi, boiling liquid expanding vapor explosion, or boiling liquid evaporation vapor explosion, occur in a closed storage tanks that contain liquefied gas. So, there are two phases in here, which is a vapor and liquefied. However, due to a fire outside the tank, this content is heated and causing increase in the pressure within the container. And when the pressure exceeds the capability of the storage tank, it will cause a failure and it will explode. So some or all of the liquid will flash boil and instantaneously become a gas.
This is an example video of how Oblivi can
When a
happen.
tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure.
Is over pressure and ready to explode.
As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion.
This is what we call as bleed.
The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion.
A fireball is made up of chemical that flash boil when the tank fills and chemical that spray out as an aerosol during explosion. Any liquid that does not participate in the fireball will form a pool fire. The primary hazard here is thermal radiation. As you can see here, this is a fireball, as same as this one. But a fireball just occurred once, and the hazard here is the thermal radiation of the fireball itself. This is an example of a fireball situation. Can you see the fireball? So how do we model this scenario, the example that you see earlier? We call it as a consequence calculation. Consequence calculation represents one of the fundamental steps in comprehensive risk assessment. This is actually a risk assessment, but we put it based on fact and figures of the modeling of the chemical itself. We calculate the possibility and the range of the explosion and the impact of the explosion. And when we get the details, we lay it out on the map and we look at the surrounding area that might be affected from the event. The evaluation of the impact area associated to all the accident scenarios are being put in here. This is a very time-consuming step. It involves hundreds and thousands of calculations. The impact area of the consequence calculation depend highly on the input. It includes the characteristic of the chemicals involved, the modalities of the release, the characteristic of the current environment condition. The combination of these different values of all these parameters will give rise to a number of accident scenarios that can happen. Each are characterized by a given value of the probability of the occurrence. If you remember correctly, risk is probability times severity. So here the consequence calculation we calculate the severity of the event, but we can characterize it based on the probability of the occurrence. Normally, consequence modeling use a Gaussian model. A Gaussian model is a model on how we predict gases are about as buoyant as air will disperse in the atmosphere. This can be a heavy gases, a jet gases, or a neutral gases. There are equations involved in modeling this. So wind and atmospheric turbulence are the forces that move this vapor in the air. So the escape cloud or the hazardous substance itself normally will blow downwind and causing a turbulent mixing, causing it to spread out in the crosswind and upward direction. So normally a Gaussian model, we will see that the plume of air are moving from a high concentration here to a more lower concentration here. In a Gaussian model, the concentration is very high at the point of release. For example, here the point of release where the concentration is very high. However, it is not diffused very far. It's at a smaller location here. However, as it moves further away from the source, the concentration decreases. It will spread more on the side itself. So this is how a gas is calculated and modeled. Different from Gaussian model, we have a heavy gas dispersion model as well. A heavy gas dispersion model is at the point of dispersion, it moves upwards. However, due the gas is heavy in density, it will move downwards into the ground area, where after that, due to the turbulence of the air, it will start to disperse. This video shows example of a heavy gas dispersion. As you can see here, the gas are moving down at the lower side. However, if this gas is flammable and when there's a source of explosion, all of this gas will caught on fire and exploded. So this will be the basic equation involved in Gaussian model and heavy gas dispersion model. The real thing is we will not be using this equation in this subject. We will only look at the chemical consequence modeling software. So we will know how to run the chemical based on the input. You will not you will not calculate this Gaussian model or heavy gas dispersion model, but you will learn how to use the software that implement these equations. There are several types of chemical consequence modeling software. There are qualitative risk assessment software, QRA, such as the safer system, the fast system, and the safety. There are fit for purpose software for emergency situation or a type of gas dispersion only, such as GASTAR or ADMS star. There are fit-for-purpose freeware as well, such as Wiser or NOAA Aloha. But we will only look at one of these software only, and I will share with you how we input the information and how do we run the gas dispersion model based on one of these freeware software. Thank you very much. This will be the end of this session. I'll see you in the next.